We're going to look at our third electric field, the polarization, but let's first review the concept of electric field intensity and electric flux density. So if we have a coordinate system, let's put a charge of Q at the origin. Now if we place another charge at some location R, that is of charge quantity Q sub t, we know from Coulomb's law that the force on Q sub t is 1 over 4 pi epsilon sub 0 Q sub t times Q over R squared in the A sub R direction. Now this is an experimentally determined law by Coulomb. He built these sensitive torsion balances and measured the forces between these charges and came up with this equation. This proportionality constant we write as 1 over 4 pi epsilon sub 0, and we'll be reminded in just a little while why we write it this way. Basically, we'll see that it is done this way so that this 4 pi does not appear in a future equation. Now, the electric field is defined as the following. If we put some charge, Q sub t, at some location in an electric field, the force on that charge Q sub t is Q sub t times the electric field. And we can see that then directly from Coulomb's law we can obtain the electric field due to a point charge at the origin as 1 over 4 pi epsilon sub 0 times Q over R squared in the A sub R direction. Now we also looked at the work of Michael Faraday and the concept of electric flux. And from his experiments we saw that he defined an electric flux flowing from a charge. So if you have a charge Q at the origin, you have an electric flux of Q flowing from it. And because of the spherical symmetry, that flux will be uniform on the surface of a sphere of radius r. So as the radius increases, the density of that flux, which is defined as the electric flux density field, will just be Q over the area of that sphere, which is 4 pi r squared in the A sub r direction. And so from looking at the electric field for a point charge, the electric field intensity of a point charge, and the electric flux density of a point charge, we see that the electric flux density field is epsilon sub 0 times the electric field. And this is why we wrote this constant in Coulomb's law as 1 over 4 pi epsilon sub 0, so the 4 pi would not appear in this equation relating the electric flux density and the electric field intensity. Now, if you have a charge and you put a closed surface around it, the flux flowing through that surface has to be the charge inside. So Gauss gave us the mathematical relationship for this observation of Michael Faraday, that the integral of d dot ds over a closed surface is the charge enclosed by that surface. Now let's place a dielectric in an electric field. So here's an electric field pointing to the right. So the electrons will feel a force to the left and the protons a force to the right. Since this is a dielectric and insulator, the electrons can't flow, but the atoms will be distorted, as the electron cloud will be pulled to the left and the protons to the right. So each atom will set up a little electric dipole as shown here. In an electric field, we can represent each of these atoms in our dielectric as a minus Q and a plus Q that are separated by some vector d, and we can define the dipole moment of each of these atoms as Q times d. Now the polarization field is defined as N times P, where N is the number of atoms per cubic meter, The lowercase p here is the dipole moment per atom. And so we see that the polarization is just the dipole moment per unit volume. Let's determine the units of polarization. So the dipole moment is a charge times a distance. So that's a coulomb times a meter. And the volume is meter cubed. So the units of the polarization is coulombs per meter squared. So we see the polarization field has the same units as our electric flux density field. And we'll see the relationship between the polarization field and the bound charges that make up all these dipoles in our dielectric is that the bound charge is equal to minus the integral over a closed surface of the dot product between the polarization field and d sub s. So the polarization arises from these bound charges. And we're going to make the distinction now that the electric flux density arises from what we will call free charges. These are charges that are not bound but are free to move. The integral of d dot ds over a closed surface will give us the free charge enclosed, minus the integral of p dot ds around a closed surface will give us the bound charge enclosed. Now the electric field is still the force that a test charge is going to experience, the force per unit charge, and that force, that coulombic force, will occur whether you have free charges or bound charges. So the integral of E dot ds over a closed surface will be the free charge enclosed plus the bound charge enclosed divided by epsilon sub 0. So here I have two conducting plates, so we can flow free charge on the two plates, say an equal magnitude of positive charge on the lower plate and negative charge on the upper plate, and everything else is a vacuum. So we have electric flux density lines going from the positive free charge to the negative free charge. If we put a closed surface like a box, and I'm showing a cross section of that, in between the plates, there is no charge within that closed box, either free or bound charges. Now let's place a dielectric between those two plates. Now we will see that there's actually a charge enclosed in this closed surface because of a movement of bound charge across this interface that's cutting through our dielectric. So let's take a look at, say, a differential element on the surface here of the box. So here's that differential surface element with the orientation normal to the surface. Each one of these dots represents an atom. Now if we apply an electric field in the direction of delta S, the electrons associated with each of these atoms will be pulled down a little bit, the proton pushed up a little bit, so we will form dipoles as shown here. Now let's look at what's happening at this interface then. Each of these atoms will form a little dipole moment. And for some of the atoms close to the interface, that will result in charges moving across the interface. For atoms that are within a distance of d over 2, where d is the displacement of the plus and minus charge when the dipole forms, those will push a charge of minus q down through the interface, whereas atoms within a distance d over 2 below the interface will push a charge of plus q up through the interface. So every atom that's within a distance of d over 2, or within this volume of d over 2 times delta S, will result in a negative charge being pushed down through this interface and an increase in negative charge in our enclosed surface. So that increase in charge in our closed volume will be minus n times q d over 2 delta S. So d over 2 times delta S is this volume. Minus q is the amount of charge pushed down through this interface for each dipole, and n is just the number of dipoles per unit volume. Now, similarly, all the charges below the interface that are within a distance of d over 2 of the interface will result in a plus q going up through the interface, which is the same as a decrease in the charge in our enclosed volume of minus q. So, this results in a change in the charge in our enclosed volume of minus nq d over 2 delta S, where d over 2 delta S is this volume in which every atom will push a plus q up through the interface, which will result in a minus q increase in charge in our enclosed surface, and n again is just the number of our atoms per cubic centimeter. So the change in charge in our enclosed volume due to just this one differential surface element delta S is minus nq d delta S. Now, if this was our delta S surface element, and instead of the electric field pointing straight up, the electric field in this region was to the right, then the dipoles will form as shown here, and this delta S surface element, there would be no change in charge, there would be no charge pushed through the interface. So when the electric field is parallel to the delta S interface, the formation of the electric dipoles does not result in any bound charge transfer through delta S. Now let's look at the situation where our electric field is at some angle with our differential surface element. So the electric field direction will be the same as the direction of these dipoles. So the angle then between the surface element and the electric field, theta, is shown right here. So this distance right here is d over 2. So the amount of movement of the negative charge down is not towards our differential surface element delta S is not d over 2, which is the hypotenuse of this triangle, but this side of the triangle, which is going to be d over 2 times cosine of theta. So only atoms within a distance d over 2 cosine of theta, or within the volume d over 2 cosine of theta delta S, will result in negative charges moving down through our delta S surface element. So the change in charge in our enclosed volume through this one differential surface element delta S due to the atoms above will be minus nq d over 2 delta S cosine of theta. So the volume, which is d over 2 cosine of theta times delta S, times a minus q moving down through our surface element, times n, which is the number of the atoms per cubic meter. Similarly, for every atom within a distance d over 2 cosine of theta below our delta S interface will result in a positive charge moving up through the interface, which is a decrease of charge in our enclosed volume of minus q. So the change in the enclosed charge because of these atoms below delta S is given by the following. minus NQ d over 2 delta S cosine of theta. So the total change in the charge due to the movement of these dipoles through this surface element delta S is minus NQ d delta S cosine of theta. And let's recognize that the magnitude of our displacement vector d times the magnitude of our surface element times cosine of theta is just d dot S, d dot delta S. And we can also recognize that minus NQ times d is just the value of our polarization field. So that's the change in the bound charge just due to this one surface element. So the total change in the bound charge inside our enclosed volume is minus the integral over that closed volume of P dot ds. So we have our relationship between the free charge and the electric flux density field, Gauss's law. We've now seen we have a similar relationship between the bound charge and the polarization field, and the electric field is associated with both free and bound charges. So now let me substitute in this expression for the electric field our Gauss's law and the result we just obtained for the bound charge. So I've substituted Gauss's law for Q, the free charge enclosed, and this expression we just came up with for the bound charge enclosed. So the electric field intensity we see is equal to 1 over epsilon sub 0 times the electric flux density field minus 1 over epsilon sub 0 times the polarization. Or rewriting this as the electric flux density field is equal to epsilon sub 0 times the electric field intensity plus the polarization. Let's further develop our understanding of this relationship between the electric flux density, the electric field intensity, and the polarization. So if we have two metal plates, such as in a capacitor, and place a charge on that capacitor, so a plus Q on this plate, a minus Q on the right-hand plate, there's no dielectric, just a vacuum. So since there's no dielectric, the polarization is going to have to be 0, and the electric flux density is equal to epsilon sub 0 times the electric field. And I'll put a sub 0 on the electric field here to designate this case with no dielectric in here. Okay, so now what we're going to do is place a dielectric in here. The plates are charged and disconnected from a voltage source, so we know that the free charge on the plates will not change, and hence, since the electric flux density is just associated with free charge, the electric flux density will not change in this region even when we introduce a dielectric. When we introduce the dielectric into the electric field between the plates of our capacitor, the atoms will form dipoles and we'll get our polarization field. The left-hand side of the dielectric will accumulate some negative bound charge on its surface, and the right-hand side here will accumulate some positive bound charge on its surface. So here I've placed the dielectric between the plates. The free charge on the two plates is the same, so the electric flux density emanating from those plates will not have changed. It will be D and will be D throughout. Here is the bound negative charge on the left-hand surface of the dielectric and the bound positive charge on the right-hand surface. So the polarization field is going to go from the minus bound charge to the plus bound charges. In these regions, there's no polarization because there's no dielectric, so everything remains the same with D equals epsilon sub 0 E. Since we now have a polarization field in here, D is equal to epsilon sub 0 times the resulting electric field in the dielectric plus the polarization. And the right-hand gap, again, will not have changed. So the electric flux density has to be constant throughout the structure, which means inside the dielectric, the electric field is going to decrease as the polarization field forms from the dipoles that form due to the electric field inside the dielectric. And so we see that we'll have a decrease in the electric field inside the dielectric because of the formation of the bound charges.